All right, hi folks. Today in this video, we're going to solve a system of equations. This is something that I'm sure you know how to do from previous math classes you've taken, but you may not have done it in a while. And it's something we're going to be doing very, very frequently. So it's definitely worth reviewing for a second. So I've written down here a system of three equations with three unknowns, x, y, and z. First thing right off the bat, in order for a system of equations to be solvable, normally it has to have the same number of unknowns as the number of equations. So when you see that there are three equations here and there are three variables, that is a very good sign that this is a solvable problem. So it probably can be solved. Now, how am I going to do it? I'm going to use the substitution method. The substitution method is not the only way of solving systems, but it's kind of the best way, or at least the most robust way. It always works for all types of systems. It's not like a cute method that only works in certain special cases. You can always use it. So most of the time, that's the way I do it, just because I know it's going to work. The first thing you do when you solve a system using the substitution method is choose which equation you want to start with. Normally, you want to choose the equation that seems like it's the simplest or seems like it's the easiest to solve for one of the variables. So for example, I think I'm going to start with the third equation because the third equation looks like at a glance it's the simplest one and will cause the least headaches for me. So but let me just kind of number the equations here so that I can reference them and you'll know what I'm talking about. So we're going to start with equation number 3. And I want to solve this equation for one of the variables. It doesn't really matter which one. Pick one that is easy to solve for and solve for it. So let's say I'm going to solve for z for no special reason. So I subtract x from both sides of the equation, and I get z equals 9 minus x. Okay, now I know the value of z. The next thing I do, now that I've solved for one of the variables, is this equation number 3 has already been used. That leaves me with two equations that I haven't used yet. So take the two equations that you haven't used yet and plug this result in. So I'm going to plug it in to equation 1, and I'm also going to plug it in to equation 2 and get rid of all the z's in all the equations. So for equation number 1, there's one z in there, so 3x, that stays the same. 4y, that stays the same, equals, now it's going to be 7 times the quantity 9 minus x, which means 9 times 7 is 63. So I'm going to have 63 minus x times 7. So 7x. And then I can simplify this a little bit. I see now I have x's on the left and on the right. So it's probably a good idea to combine those and make it 10x plus 4y equals 63. Okay, so there's my new equation 1. In this particular system, equation 2 doesn't have any z's. So there's nothing to do in equation 3 and equation 2 because I'm only worrying about z's right now. So equation 2, I'm just going to copy. I would substitute out any z's if there were any, but instead I'm just going to copy down. So now these two equations here are now a system of two equations with two unknowns. So you'll notice I used one equation to eliminate one variable, and I went from a system of 3 equations with 3 unknowns down to a system of 2 equations with 2 unknowns. Now you just repeat this process. Now I have a system of 2 equations with 2 unknowns. Pick one of those 2 equations. I've got here number 1 and number 2. Number 2 looks easier, so I think I'm going to pick number 2. Okay. let me just start fresh over here. I'm going to pick number 2. Y, it looks like y is easy to solve for. I can pretty much do that in my head. So I'm going to do y equals 8x minus 4. Okay, I move the y to the right side of the equation. I move the 4 to the left side of the equation. And now I've got that one solved for y. So now I'm going to substitute this result into equation 1 to get rid of all the y's. So equation 1 now becomes 10x, that can stay the same, plus 4 times 8x minus 4. I'm going to write it out longhand this time. And then the 63 can be left alone. Distribute that 4 through, so I'm going to have 10x plus 32x minus 16. I'm multiplying everything by 4 equals 63. 10 plus 32 is 42. And move the 16 to the other side of the equation. 63 plus 16 is what, 79? And now I can solve for x. 79 over 42. 79 over 42 is 1.88. Okay. You'll notice, by the way, what I did systematically here, I started with 3 equations with 3 unknowns. Then I got rid of z and made it 2 equations with 2 unknowns. Then I got rid of y and made it 1 equation with 1 unknown. Then I can solve that. Now we're going to reverse that process. I now know the value of x, so I bring this back. This is also why it's important to have neat work when you're solving systems of equations, because I'm going to recycle all that work when I work my way backwards now. I now know the value of x, so I'm going to put that back into the equation that I have here. So now I have y equals 8 times 1.88 minus 4, which is 8 times 1.88 minus 4 is 11.0. So there's your value of y. Now I go all the way back to the beginning, to here. And in this case, there was no y in that equation. So I'm going to take my value of x and plug into that equation. I would also plug in my value of y if necessary. But so I'm going to have z equals 9 minus x. So 9 minus 1.88, and that gives me 7.12. Okay. And now I have the values of all 3 of those variables. And that's how you handle a system of equations using the substitution method.